Yes, I'm back now. I'm just going to share my screen. Are you able to see my screen, and is it full screen?
Yes, yes.
Yeah. Okay. So let's begin. Sorry for the delay. Let's start. Okay. So we have thought of quasars as point sources so far. But quasars have host galaxies. They are just very bright nuclei which are outshining the galaxy by a factor of 100 or more. Now, the reason we can't see the host galaxy is that the full width at half maximum of the point spread function of typical ground-based observatories is about 1 arcsecond. At z equal to 2, the angular scale is about 8.5 kiloparsecs per arcsecond. So even if you have a fairly large galaxy like the Milky Way, can anyone tell me what is the diameter of the Milky Way in kiloparsecs?
It's 10 kiloparsecs.
No, it's more like 30 kiloparsec or 100,000 light years, 1 lakh light years, or 30 kiloparsec. So that's the diameter of the Milky Way. We are located about 8 kiloparsecs away from the center of the galaxy, from Sagittarius A star. So even if you take a large galaxy, a 30 kiloparsec galaxy like our own, and place it at redshift 2, it will have an angular size of between 3.5 to 4 arcsecond, which is really very small. And given the point spread function of 1 arcsecond, that is just the full width at half maximum. And if the quasar is 100 times brighter, then it will just wash out the light from the host galaxy, and you'll never be able to see it. So the question is, so it's a difficult situation. Is there any hope of detecting a quasar host galaxy directly? So how would you do this? I mean, the hints are in the information that I have given you here.
Sir, we can use, hello?
Yeah, go ahead, Manish.
Yeah, sir, we can use space-based telescope.
Yes.
In which...
and why is space-based telescope better?
Because in the ground-based telescope, there will always be, the minimum will be 1 arcsecond of seeing due to the atmosphere.
Correct.
In the space-based telescope, we can increase the resolution. Because there is, we can increase the resolution by constructing a telescope which is not obstructed by the atmosphere.
Correct. And do you know what kind of, so what you're saying effectively on the surface of the Earth with an optical telescope, you are limited by the atmosphere. So this is called seeing limited conditions, right? But once you go above the Earth's atmosphere, this atmospheric seeing is out of the picture, and then you are going to be diffraction limited, right? So does anyone know what would be the diffraction limit of, say, a 1 meter telescope in space? So you can work it out just using 1.22 lambda by d would be the resolution, correct? And lambda you can take as 5,000 angstrom, d you take as 1 meter, and then you'll get the answer in radians, convert that to arcsecond, and you'll see it's much smaller than an arcsecond, right? In fact, for a 1 meter telescope, you will get a tenth of an arcsecond. And remember, the Hubble Space Telescope is a 2.4 meter telescope. So you will go a factor of 2.4 better than that. So you will be much smaller than, you'll be much, your resolution will be better than 0.1 arc second by a significant factor. Right. Is there any other advantage in space?
So we can get the UV spectrum.
Yes, you can observe it in the UV. That is correct, because very much harder to do it from the ground. And also another thing that happens is the atmosphere generates something known as air glow, which means that there are photons coming in from outside. There are also photons being emitted from the earth, unfortunately, what we call as light pollution. These photons get scattered, right? And when they get scattered, the sky does not remain absolutely dark. It has some atoms that are either scattering light or even emitting light. So if there is a high energy photon that comes in and gets absorbed by the atmosphere, that high energy photon will excite certain atoms and molecules in the atmosphere, and they will radiate again, and that will give out light. So because of this air glow, there is a certain brightness that is there. The sky is not absolutely dark, it is less than absolutely dark, and therefore detecting faint extended objects becomes even more difficult. So we are not able to see those faint host galaxies. So going to space certainly helps in two ways. One big thing which Manish has mentioned is the point spread function improves drastically. The sky brightness improves drastically, right? Is there any other thing? Can you do something about the angular scale being 8.5 kpc per arc second? Will it help to observe a lower redshift quasar? Naturally, right? Because two things. One thing that will happen is that the pixel scale will change, and therefore you will be able to see the host galaxy more easily, because the angular size of the host galaxy will be larger. The angular scale is going to change in your favor. So this is exactly what was done in 1997 by John Behcall and collaborators. So what they did was they said, okay, we absolutely have to use the Hubble Space Telescope. And let us not look at redshift 2 quasars. Let us look at redshift 0.3 quasars, right? And they looked at several objects which were at redshifts less than 0.3, and they could clearly detect the host galaxy. Okay, so now at the center of each of these panels is the quasar, and you may see the diffraction spikes from the stellar source at the center. In some of them, you can see the diffraction spikes here. Okay. Now, one thing you will immediately notice is that the morphology of these objects, except for this one, which looks like a nice elliptical galaxy, the morphology of many of them, it looks a little bit disturbed, and some of them look clearly like merging galaxies. Okay, like this one or this one. And here you can, I'm not sure you can see it on your screen, but there is some tidal tail type feature on this side. And here there's a lot of diffuse emission, which is coming from a much larger region. Okay, so they were indeed able to detect for the first time host galaxies of quasars, thereby indicating that quasars were essentially the central regions of galaxies. They were not some exotic special object. Okay, so this idea that mergers may be responsible for fueling quasars is not a very new one. Many people thought that that seems to be the easiest way of keeping a quasar going, right? And this will also explain why quasars were more common at redshift of 2 than they are today. So these active galaxies require fuel to stay active. Unless you can keep on channeling gas and dust and stars close to the accretion disk of the supermassive black hole, the quasar will switch off at some point if it runs out of fuel. Merging galaxies are an efficient way of channeling gas and sometimes stars as well towards the center, right? Galaxy mergers were very common at earlier epochs. We do know that. And because of that, it is very likely that since mergers were more common, there was ample gas that could be channeled towards the central regions. And therefore, the supermassive black holes could remain much more active than they are today. We know that. We know that for sure, that the co-moving number density of quasars in the local universe is much smaller than what it was at redshift 2. Okay. So mergers are one way of sort of growing the black hole, right? Or fueling or feeding the black hole. Are there other ways in which it can happen? So let's look at a slightly broader picture, which is the growth of bulges in spiral galaxies. This could also hold more or less for elliptical galaxies as well, at least the first part. So how do you build up the spheroidal component of galaxies? The first way is something known as rapid collapse. There's a primordial hydrogen cloud. It's very large in size. It begins to collapse under its own gravity and builds up a large bulge of stars, of old stars, because this happened at very early epochs. These stars were built up very, very rapidly. So at some very early epoch, the bulge grew very rapidly, but then at some point the gas got used up and the bulge stopped growing. The second thing is, of course, we've looked at already, is environmental effects of mergers, major mergers or minor mergers. So here they've shown what is called as a major minor merger. So there is a big disk galaxy, and a smaller galaxy falls into the disk galaxy. And then the bulge grows because that smaller galaxy brings with itself gas, which can get converted into stars. And that's how the bulge grows. The third way is what is referred to as internal secular evolution, wherein the galaxy grows without any input of gas from outside the galaxy, right? It's sort of, there's a disk galaxy, and disk perturbations form bar-like structures which channel gas from the outer regions to the inner regions. And then the bulge grows with new stars. The bar can get disrupted and destroyed and dissipate. And so the bulge grows from using the gas of the galaxy itself. Now the question arises that if we have a supermassive black hole at the center, will these processes also lead to an increase in the black hole mass? So what do you guys think? Will it or not?
I think yes.
Yes, right? Will all the three processes, can they lead to the growth of the black hole?
Yes.
Yes, in general, except for the first one, you may not have a black hole to start with, right? So there is a lot of debate in the literature, is that how did the supermassive black hole form in the first place? We have various mechanisms that say that, okay, once the black hole forms, we have ways of feeding it material and its mass will keep on growing. That is not the problem. But how does the seed black hole form? Of course, we won't go into that in this course, but there are many mechanisms. One may be that there could be just a few stars. So you start off with a stellar mass black hole at the center, and then that gradually accretes more and more matter, and over time becomes a supermassive black hole. Right. Okay. So now let us look at, if you want to measure the SMBH mass, we've already looked at how we could make a measurement like this in one of the early lectures, where I said that one could use the virial theorem, measure the velocity dispersion of the gas that is in the AGN, get some estimate of the size of the emitting region and put that as R, and there you get your mass. That's how we got a rough mass of about 10 raised to 8 to 10 raised to 10 solar masses for the black hole. And this was done very long back, about 50, 60 years back. Now, in this measurement, what would be the biggest source of error even today?
I think it's R.
Correct. And why is R uncertain?
Because we don't know how much the galaxy is extended, because it also contains gas which do not emit light, and we generally dependent on the light to measure the sizes.
Correct. That's one way. Yes, definitely. So you don't know which of it is AGN light, which of it is galaxy light, and so on. Are there any other sources of error?
Yes, sir.
Yeah.
Sir, the luminosity distance cannot be computed exactly. The accuracy is very poor.
Yes, yes. It's not very poor nowadays, because we have measured 50, 60 years ago, it was luminosity distance would be off by uncertain by a factor of 2, right? But now it is much less uncertain, maybe about 4 or 5%. And that is because the Hubble parameter has been measured to that accuracy. So so for R, would you need luminosity distance or some other distance actually?
So you might need the angular size distance.
Yes. Okay. So you would need the angular diameter distance. Okay. That is the distance to use, not the luminosity distance. When you are measuring an angular size and knowing the distance, you are converting that to a physical size. You need to know that, not the luminosity distance. Correct. Right. So the uncertainty in R is the biggest uncertainty that we have for both of these reasons, that we can't actually specify that this is the region from which the light is coming, and all of it is dominated by dispersion caused by the AGN, and R itself being uncertain because of uncertainties in the cosmological angular diameter distance. Okay. So now,
Sir,
let us forget. Yeah, go ahead.
sorry, central black hole mass is changing. So can we use the virial theorem? Because
the black hole mass is changing. We can use the virial theorem, because remember, we are not making a measurement of a quantity that is changing very rapidly with time. So it's not as if today you measure it and R was something, and 3 months later R has doubled. It's not going to be like that, right? Because the accretion rate is limited. The accretion rate can never be higher than a certain rate, right? So for all practical purposes, you can assume that at the time you make that measurement, the situation is stationary. You're right. I mean, if the mass were continuously increasing very rapidly, then this is not an equilibrium situation, and the virial theorem will not hold. But for all practical purposes, because the rate at which the mass is increasing in terms of percentage increase per year or per century is very, very small. Okay.
Yes.
So now, is there a more accurate way to measure the SMBH mass for the nearest dormant SMBH to us?
Hello, sir.
Yeah, go ahead.
Sir, I don't know if it is accurate, but the mass which is measured of the black hole mass, which is measured by Andrea Ghez and Reinhard Genzel by the technique of looking of the motion of the nearest stars to the black hole, maybe it is the way to measure, but I don't
Yes.
know how accurate.
Yes. Yeah. In fact, that is quite accurate. It is in fact much more accurate than the velocity dispersion of the gas, which is measured over a much wider region. Because what they're able to do with these stellar orbits, and I need to show you a video. So what they're able to do is actually track individual stars in their orbits around the supermassive black hole at the center. Okay. And this is a video. These are actual stellar orbits in 3 dimensions, which are shown here. Of course, there are some uncertainties in the 3rd dimension, but as you can see that stars, as they approach the center, which is somewhere here, there is a lot of speeding up of the stars, right? Which is exactly what you would expect from Kepler's laws. Now, this little gas cloud which came and got disrupted, this is an animation which was made when a gas cloud was some years ago, about 5-6 years back, was supposed to go and fall into the black hole. And of course, that would have led to a spectacularly bright flare from Sagittarius A star. But that somehow didn't happen. I think it didn't come close enough to get disrupted. So this animation was for that gas cloud to come in. But for over 2 decades, using both or nearly 3 decades now, Andrea Ghez, Reinhard Genzel and collaborators, who won the Nobel Prize last year for their work on black holes, on supermassive black holes, specifically at the one at the center of our galaxy and in some other galaxies. They actually use this technique of tracking individual stars, right? And this was so you can use, again, you can just use the virial theorem here and measure the orbit. Right. So can one measure the mass of the sun using the speed of the Earth's orbit around it? Would it satisfy the virial theorem?
Yes.
Yes, absolutely. Because a completely equilibrium system hasn't changed for millions of years. No problem. So I just plugged in the values. The speed of the Earth in its orbit around the sun is about 30 kilometers per second. And I plugged in the 150 million kilometers as the radius of the orbit, plugged in the value of G, and I got the mass of the sun pretty accurately. No surprises here. So this is the exact technique by tracking the orbits, the elliptical orbits of stars around the supermassive black hole at the center of our galaxy within a few percent. And especially if you have multiple stars which are all coming close, that accuracy improves even further. So to about 1% or so, we are able to measure the mass within that volume, which the nearest star comes to, the shortest radius from the center, and get a fairly accurate mass. Now, I showed you a picture from the Event Horizon Telescope in one of the earlier lectures. So there is now a new technique. So earlier we were using basically the velocities of individual stars or the velocity dispersion of gas or stars to measure the mass of the black hole. But it was done in a newer way using the supermassive black hole at the center of M87. Does anyone have any idea how that could be useful? This few letters here may give you a clue.
Hello, sir.
Yeah.
Are you asking about how the mass was measured from the
How was
black
the
hole
mass
picture?
of M87 measured? Of course, it had been measured earlier using the velocity dispersion technique that has been used for 50 years. But recently, when they got the Event Horizon Telescope image, they were able to use the Event Horizon Telescope data to make a more accurate measurement of the black hole mass.
I think if they were able to measure the event horizon size, which is Schwarzschild radius of
Yes.
the black hole, calculating mass will be easier from that. But
Correct.
I don't know how they measured the event horizon from the picture of black hole.
Yes. So as I told you the other day, the event horizon is not very sharply delineated. Okay. And there are all kinds of general relativistic effects. But what they tried to do was to build a model of the accretion disk around the black hole and use techniques from GRMHD, which stands for General Relativistic Magnetohydrodynamics, and use a GRMHD simulation to predict the kind of image that they would expect to see, assuming some kind of optical depth and sort of optically thin plasma, etc., etc. And then they put in various, the main input parameter would be the mass of the black hole. So you keep on changing the mass of the black hole and see what the magnetohydrodynamic simulation predicts for the emission that you will see, right? And the emission will also be need to be modulated by lensing effects. I told you that because of strong gravity at near the Schwarzschild radius, the image gets very strongly distorted. So you have to use gravitational lensing formulae to actually distort the galaxy, distort the region around the Schwarzschild black hole, and predict what the image will look like. And using all of these techniques, they've written a nice paper on this in 2018 or 19, and where they describe the general relativistic magnetohydrodynamic simulations and how they were used to get a more accurate estimate of the black hole mass of M87. M87 is not a quasar. It's a radio galaxy, but it is, unlike our own galaxy, it is an active AGN. Right. So now, we've looked at techniques to measure the mass of the black hole. We have some handle. We have some relatively inaccurate techniques, and we have some relatively much more accurate techniques. But suppose you wanted to measure the total mass, including dark matter of a galaxy. How would you do it?
Hello, sir.
Gravitational lensing.
Gravitational lensing, but most galaxies will not be will not show you any strong lenses, so that may be harder. Any other ideas?
From the rotation velocity curves, we can measure.
Correct. That's absolutely right. So one would use the rotation curves of galaxies, either in the optical or in the radio. In the radio, if you can see the neutral hydrogen emission, then you can plot the rotation of the neutral hydrogen. And from the velocities you can estimate how much mass is enclosed within different radii. So by using the rotation curves of galaxies, you can measure the mass. And of course, you're here measuring the gravitational mass. So you are going to pick up the dark matter content as well. But suppose I said, no, forget about dark matter. I want to measure only the stellar mass of a galaxy. How will you do that?
Hello, sir.
Yeah.
Sir, for measuring stellar mass, I guess we can use mass to light ratio, and if we have a mass to light ratio fixed, we can use a present day initial mass function from the initial mass function to calculate what is the distribution of the stars, and in that way we can measure the stellar mass.
Yes. So you are absolutely on the right track. So there are techniques called stellar population synthesis techniques. Okay, in these, what one does is that one sort of assumes the initial mass function, one assumes a star formation history, one assumes then that the galaxy is of a certain age, etc., and evolves the galaxy in time and calculates the buildup of stellar mass. Okay, remember, some of the stellar mass will continue to be in the form of stars, but some of it will be in the form of remnants, stellar remnants, like white dwarfs, black holes, stellar mass black holes, neutron stars, etc. And you count all of that, and then you find out how much mass you have. And then how will you validate it? You will take a model, make a prediction of how many stars of a certain kind should be after, let's say, 10 billion years, and then compare that with the light that you see from the galaxy, right? So this is a more sophisticated way of measuring the average mass to light ratio of the galaxy as a whole, right? By just integrating over each individual star. Because remember, the mass to light ratio of the galaxy is a weighted average of the mass to light ratio of each individual star, which is different, right? Bright stars, luminous stars have different mass to light ratio than, say, sun-like stars, right? So you can measure the stellar mass reasonably accurately. Nowadays, with stellar population synthesis techniques, it is routine to measure stellar mass to within about 10% accuracy. Okay. So now, some years ago, very interesting relations were found between the velocity dispersion in the central region of the galaxy, which is plotted on the x-axis, and the black hole mass. Okay. And this is not totally surprising, because you would expect that there is some kind of correlation. But remember, this correlation now is not the stellar velocity dispersion of the gas that is in the AGN. Many of these galaxies shown here are in fact not AGN. Okay, they are just normal galaxies. So the velocity dispersion is over a much larger region, say the central kiloparsec or so. Okay, not the central parsec or so. And so because of that, one is measuring really the velocity dispersion of the stars at the center in the central regions of the galaxy. And one is measuring basically the gravitational field over a much larger region, right? So it's not really the velocity dispersion caused by the AGN or by the black hole. It is the velocity dispersion of the central region. And the black hole mass was determined using any of the techniques that we spoke about. And there seems to be a fairly strong correlation between the mass of the black hole and the stellar velocity dispersion. This was first reported by Megorian. So it is called as the Megorian relation, but is also referred to in the literature as the M sigma relation. Mass of the black hole seems to be correlated with the velocity dispersion in the central regions of the galaxy. What was also found around the same time, about 20 years back, is that the bulge mass is also correlated with the mass of the supermassive black hole. Now, this is a little surprising because remember, the bulge is a very large entity. It's 10 kiloparsecs or so in size. The black hole is sitting in the central milliparsecs, right? But this seems to indicate that the growth of the bulge and the growth of the supermassive black holes occurs through similar processes, possibly even at similar times. And this is not totally, in fact, this is quite consistent with our understanding of how bulges grow. Remember that the slide that I showed you earlier, this one, right? The processes that grow the bulges of galaxies may be the same processes that grow the mass of the supermassive black hole at the center. And that is the reason you do see a direct correlation between the luminosity of the bulge. These are what's plotted on the y-axis is the absolute magnitude of the bulge in the V band, right? And the mass of the black hole. And this correlation seems to more or less hold, whether you are looking at quasars, whether you're looking at galaxies, whether you're looking at Seyfert-1 objects or Seyfert-2 galaxies. Okay, these are the two types of Seyferts. We have still not introduced types of AGN yet, but you'll see them in probably the next class. Okay. Right. So now this leads us to the last sort of next follow-up question. We found that black hole mass, velocity dispersion in the central regions, and the luminosity or even the mass of the bulge are all correlated, right? Now, is the quasar luminosity correlated with the supermassive black hole mass? Because if it is, that gives us a very cheap way of measuring the mass of the supermassive black hole. So what do you guys think? Is it correlated or not? So it turns out it's not very strongly correlated, very poorly correlated, right? There is some weak correlation, but it's really the scatter is very large. And why do you think the scatter is large? Which parameter will determine the luminosity of a quasar? Independent of the black hole mass.
Age of the quasar.
Age is one, but let me give you a hint. See, there are the Milky Way supermassive black hole is 10⁶ solar masses, right? But its luminosity is very low compared to some other AGN, which host a black hole of the same mass but are much more luminous. What is the difference between Milky Way and this other galaxy?
Maybe the gas accreting the.
Yes, yes. So the gas accretion rate is the determining parameter, right? So if the gas accretion rate is 0, it doesn't matter how big the supermassive black hole is. It will just be quiet. Its luminosity will be, the quasar luminosity will be 0, right? But is there an upper limit to how much gas can be accreted? Is there an upper limit on the mass and luminosity of stars?
It's adding to luminosity.
Correct, correct. So what happens is, as the star becomes more massive and it becomes more luminous, but as it becomes more luminous, the outward force from the radiation pressure becomes higher and higher and higher. And eventually a stage is reached that the gravity is no longer enough to compensate for this opposite effect, and a maximum luminosity is reached. So this is referred to as the Eddington luminosity. So similarly, for quasars too, we do have Eddington luminosity. There is an Eddington rate for mass accretion, you cannot accrete faster than that, because then the quasar becomes so luminous that it starts to drive away the infalling matter. And so there is a limit to the maximum luminosity of a quasar, and that is more or less at about the bolometric luminosity of about 10 raised to 48 ergs per second. It's not possible to build quasars that are more luminous than that. Okay. Now, once people discovered host galaxies, they started looking at the properties of those host galaxies. And they found that for nuclear luminosities which were brighter than MV minus 23.5, the hosts of both radio loud and radio quiet AGN are all massive ellipticals, right? And this statement generally holds that if you take the most luminous quasars, they are hosted by galaxies that look like ellipticals. The radio morphology, whether it's radio quiet or radio loud, does not seem to have an effect on the luminosity. So on the morphology. So the morphology seems to depend on the optical luminosity, but does not seem to depend on the radio luminosity, because there are many objects which are quiescent, evolved low redshift ellipticals of comparable mass, right? So it does not correlate with radio loudness. Also, it doesn't correlate very well with the optical luminosity. I mean, in the sense that you can have a non-AGN, which is an elliptical, but you cannot have a very luminous AGN, which is not an elliptical, hosted by an elliptical. But if there is no, if it's in the quiescent phase, yes, you can have elliptical galaxies which are quiescent. The fraction of massive spheroids or black holes that produce quasar level activity, it seems to be about 0.1% at the present day, rising to greater than 10% at Z between 2 and 3. So this also has been confirmed, that if you take the local universe and just count how many of them are showing quasar level activity, they may be weaker AGN. We will come to those in later lectures, but very strong luminous AGN like quasars, they are there only in about 1,000th of the elliptical galaxies in the local universe. But they're in there at the 10th, greater than 10% level. So more than 10 times, sorry, 0.1%. This is 1 in 10,000 galaxies is in the local universe. Elliptical galaxies is a quasar level AGN. And this rises by a factor of 100 once you go to high redshifts. Okay, so this is a plot of the number density of quasars over time, right? And what is shown here in triangles, red triangles, are the optically bright quasars. And these are the quasars that we are preferentially finding at the highest redshift. There are also X-ray techniques that can be used to search for quasars. It's not very efficient. You can only find a few, but you can use those to estimate what the number density is, depending on whether they are bright or faint in the thing. And remember, whenever you calculate a volume density of quasars, you must calculate a co-moving volume density, right? Because the universe is expanding, you have to take that into account. So you always talk of co-moving gigaparsec cube or co-moving megaparsec cube and so on. Okay. So now let us ask a question which we could ask based on what we've learned so far. So I told you earlier that initially people said while looking for quasars, start with radio sources, then look for a point like optical source, check if that source is blue, okay, and then go and get its spectrum, right, to confirm it. So we relaxed that radio requirement and we found 10 times as many quasars as we had found with the radio technique. So these are just UV excess star-like objects whose spectrum confirms that they are they're quasars. These are the radio quiet quasars. So can we relax that blue requirement, UV excess requirement? Could there be a population of quasars that do not exhibit a UV excess? Can you think of any way a quasar could be there? It could be luminous, but it's not blue.
They're extremely UV photons. They may like ionize the gas around, so you don't get that. You don't get that part of the spectrum.
Correct. So what would it need to be? I mean, would it need to be optically thick to UV photons? The surrounding material?
Yes, yes, it should be optically
It
thick.
should be optically thick. Then it would absorb all the UV photons, right? And then you would not see the UV photons at all, and there would be no UV excess. So what's the most efficient way of absorbing UV photons? Even at relatively low densities?
If it's lesser than like 912 nanometers, then the hydrogen atom.
Yeah, no, that's true. But I mean, what material would absorb UV photons quite easily?
So dust.
Dust, right? That's the reason the sun at sunset is red, right? So this population of quasars is referred to as type 2 quasars or optically obscured quasars, right? We'll come to a little later why they're called type 2 quasars, but just remember that these type of quasars are called type 2 quasars. When I talk about type 2 Seyfert galaxies, you will understand why these are called type 2 quasars. Okay, why are they hard to find? They're optically faint. So any flux limited sample that you construct, if suppose you say I'll start with all star-like objects brighter than 18th magnitude, because they're dust reddened, they're also much fainter in the optical because the dust will also absorb all other optical wavelengths, right? So you will not see, you will not find them to be very bright. You will find them to be quite faint. So your samples will miss them. These quasars, again, this is something that when we talk of the unification model, you will understand, but why this is so. But they have typically show absence of broad emission lines. And because of this, if you're using a relatively low resolution spectrograph, which is only sensitive to broad emission lines and not to narrow ones, these kind of spectrographs will completely miss, even while taking a spectrum, even if you have a candidate and you take a spectrum, you will say that, no, this is not a quasar because the emission lines are not seen. Because there are no broad emission lines in these objects. They're also weak in soft X-rays, which tends to get absorbed by dust. Hence, if you have an X-ray selected sample, that too is going to miss them, right? So we'll talk a bit more about obscured quasars in the context of the unification model a little bit later. But now, so can you think of any technique that you can use to find these objects? So optically they're weak, in X-ray they're weak.
in the IR region?
Yes. So the UV photons that are absorbed by the dust will the dust will get heated up because of that, and it will re-radiate at IR wavelengths. Now, depending on the temperature of the dust, if it is hot dust, then it will emit in near and mid IR. If it is cooler dust, it's going to emit in the far infrared. But yes, so the UV excess will not be there in these quasars, but it will manifest as infrared excess. And those kind of techniques can be used, and particularly after the advent of the Spitzer Space Telescope and the WISE telescope, people have used infrared selection techniques to try and find this population of obscured quasars. Very few have been found so far, of the order of 1,000. Okay, compare this with the 750,000 unobscured quasars that we know of. So clearly these are either very rare objects or we haven't found them. But by comparing the luminosity functions of these objects with the luminosity function of the type 1 quasars, people find that people are able to estimate their number density, and that seems to be comparable to the number density of the type 1 quasars. So we are missing about half the quasars in the universe because they are optically obscured. Okay, so now, was there any question?
Yes, sir.
Yeah, go ahead.
So type 2 quasars are same objects as quasars, just that they are obscured by dust, or they are intrinsically different?
Okay. So I'll answer this question, but we'll look at the details in the unification model. They are the same kind of objects. You are just viewing them from a different viewing angle that takes you through your line of sight through the dusty torus that surrounds the accretion disk. So if you're looking through the dusty torus, the same quasar will appear to you as an optically obscured quasar. And that is why people are not so worried about missing them, because their inherent properties are exactly the same as the type 1 quasars. At least that's what the unification model believes. Okay. Now, a few more little detours about quasars, and then we'll stop. Quasars can be nicely gravitationally lensed. Okay, so what you see here is at the center, this sort of yellowish object is the galaxy which forms the lens, and in the background is a quasar which has been lensed into 4 images. Okay. Now, if it were completely symmetric situation, you will see the full Einstein ring. But in this case, things are a little bit offset. So you see 3 images on one side, 1 image on the other, and so on. And but these are gravitationally lensed objects. And by measuring the geometry of the lens, one can even measure the Hubble parameter. Okay, and how is that done? Remember, many quasars are variable, right? And if you know that one image, let's say, changes brightness now, and another image changes brightness 15 days later, and a third image changes brightness a month later, you know how much is the difference in the optical path of the quasar, and that will help you determine the geometry. Remember that there are 2 uncertainties here. One is the what is the mass distribution of the lens, and the second thing is what is the actual physical distance as measured by, let's say, the luminosity distance that the quasar light has traveled. And that, of course, depends on your cosmology. So in principle, it's possible to even measure cosmological parameters by measuring the light delays in the lensed images of the same quasar. Okay, so now another interesting thing. So many years ago, we found these two quasars, okay, which were right next to each other. We didn't discover the quasars, we just studied their radio properties. And the question that was being asked was, are these gravitationally lensed or not? Okay, now if you took the spectrum of both of these objects, they had the exact same redshift. If you looked at the spectrum itself, it was very, very similar between the two objects, right? So the question was, are these gravitationally lensed images of the same quasar, or are these two quasars that are physically close to each other in space? So we used radio data to conclusively prove this in one way or the other, right? So how do you think radio data may be used to distinguish whether these are lensed images of the same quasar or two different quasars?
Hello, sir.
Yeah, go ahead.
I don't know if radio interferometry is a thing, but if these are two different images, they maybe produce interference pattern in radio. I don't know. I'm just guessing.
Oh, no. Which are two different images?
They are two different quasars.
Right.
So if there is something, I don't know if there is something exists like radio interferometry or something. I don't know.
Yeah. Radio interferometry will give you an image in the radio of both of these quasars, right? I haven't shown you the radio image because that would be a giveaway. Okay.
The structure will be same if they are same from the same source.
They're both point sources, so there is no structure. In the radio also, they are point sources. So really, there is no structure you can see, because you can see these two objects are there. This is quasar 1 and this is quasar 2. Or image 1 and image 2 of the same quasar. One thing that was there is, in a gravitationally lensed situation, normally the separation is not so large. It is only about 2-3 arc seconds at most. This separation is about 10 arc seconds. So that was already sort of reasonable indicator that these are not lensed quasars. But we confirmed it in a very, very unambiguous way. Tell me one thing, what is the wavelength dependence or frequency dependence of gravitational lensing?
It doesn't depend on wavelength or frequency.
That's absolutely right. Okay. So that was the thing that helped us nail it. So what that tells you is that since gravitational lensing does not depend on frequency or wavelength, then the amount of lensing that the radio photons will undergo will be exactly the same as what the optical photons undergo. So suppose these are lensed, okay? Then if you take the ratio of the flux of these two quasars, let's say quasar 1 divided by quasar 2 in the optical, and compare it with the flux in the radio, then you have the clue. So what we found was this quasar is about 10% brighter than the other, right? But its radio flux, the radio flux of this guy is actually about 9 times higher than the radio flux of this one. And that is not expected. We don't expect a wavelength dependence. So if this one is 10% brighter than this, if it were lensed in the radio, the lensed radio image of this one will be 10% brighter than this one. And it wasn't the case. Actually, this one was 9 times brighter, at least, because this one was not detected in the radio to our flux limit. And this was 8.9 millijansky.
Sir,
right?
but what if there is some cloud in one of the path and that is absorbing some rays?
Yes, yes. So it turns out that radio is one of the best frequencies for finding dust obscured objects, because at radio frequencies, dust is nearly transparent. Okay, because the wavelength is so long, it just goes through the dust. So
But
there
we
is
are
no,
also taking optical ratio, right?
oh, the optical ratio, one of them is very faint. Yes, yes. So that would be a real compensator, in the sense that you're saying that one is actually 10 times brighter, but it has been faded by that much. That too you can estimate, because if a quasar light is absorbed by dust, its overall flux changes, but its color also changes. It's impossible to absorb light without changing the color. And the color of these two quasars is nearly identical. And the spectra is also nearly identical. And the spectra both show UV excess, indicating that these are both unobscured quasars. So all of those explanations went away, because there is no other explanation. And the fact that gravitational lensing doesn't depend on wavelength. If it had some dependence which was not precisely modelable, we would be in trouble. Okay, so I think I'm going to stop here. If there are any questions, please ask. Otherwise, we'll continue in the next lecture.
Sir,
Yeah.
so is there any reason like why we found most of the quasar in elliptical galaxies?
Why do we find most of the quasars in elliptical galaxies? Is related to the fact that most massive, we are not saying most of the quasars are found in elliptical galaxies. What we are saying is most of the luminous AGN are found in elliptical galaxies. And that is related to the fact that the growth of the bulge and the growth of the supermassive black hole, they occur simultaneously. So if you build a very, very massive black hole, you simultaneously build a very, very massive galaxy. Now, whether that black hole is quiescent or not will depend on the conditions there. But if the black hole turns on, then it has the possibility of becoming much more luminous. So there is also a dependence on mass. It's not just a pure dependence on accretion rate. So if you take a maximally accreting 10 raised to 6 solar mass black hole, that is going to be much fainter than a maximally accreting 10 raised to 9 solar mass black hole. Correct? So the most luminous quasars therefore also sit in elliptical galaxies, because the most luminous quasars are maximally accreting black holes, which are billion solar mass black holes, which are very massive black holes. That's the reason you find that. But there are black holes that are sitting quietly, billion mass black holes, which are sitting quietly at the center of elliptical galaxies. I hope that answers your question. So very briefly, you can have billion mass black holes only in big elliptical galaxies, not small elliptical, big massive elliptical galaxies, because these are the only galaxies that have sufficient large bulge mass, which co-evolves with the black hole mass. Every massive elliptical galaxy is not going to be a quasar, but every quasar is going to be sitting in a bright elliptical galaxy. Okay, so if there are no further questions, we will break for now and meet again at the same time on Wednesday.